So, hello everyone. I am Anuj Kumar. I am a PMRFTA for this course, Coordination Chemistry. And today I will be discussing assignment 11 for this course. Okay. So, the assignment 11 is related to uh, basically some reactions, reactivity. Okay. But the LFT and sigma, some concepts related to sigma and pi orbital bonding. Okay. So these are the first two problems for today's session. First one is asking about in octahedral metal complex, the ligand group orbitals capable of pi interaction belongs to the which symmetry class? Okay, so here are some triplet types of symmetries are given. First one is T2Z, T1U, and T1Z, and similar all options are there. You have to identify. Okay, and the second is about it is a chromium tetracarbonyl complex. You have to determine the T to Z orbital of metal center participate in pi bonding with uh, vacant d pi orbital of ligand, vacant pi star, that is anti-bonding orbital of ligand, vacant pi orbital or filled pi star orbital of ligand. Okay, so these concepts are already discussed in the class. So just let me know if you know the answer for these two problems. Otherwise, I will discuss. Okay, I'll wait for your responses for hardly for 2 minutes. Okay. Okay, so let me discuss these. So, in a octahedral metal complex, the ligand orbitals that are perpendicular to this bond axis are capable of pi interaction with the metal orbitals. Okay, you know, in the octahedral metal complex formation, there are basically six ligands. Okay, and 12 ligand group orbitals are available. Okay, these orbitals are having symmetry T2Z, T1U, T2U, and T1Z. Okay, but basically, uh, the orbitals that involved in pi bond formation is T2Z, that is basically combined with the ligand orbitals and form one bonding, and one is anti-bonding orbitals. So there are total uh, 12 orbitals. Okay, and what about the second one? Okay, so An important factor that contributes to the high ligand field strength of ligands, such as this sigma donor pi acceptor, is pi donation between the metal and ligand. Okay, so there are three types of pi bonding on in metal complex, and most situation is when a ligand such as this donates. Basically, it is a sigma donor pi acceptor ligand. Okay, so while it accepts the electron density from the metal through a overlap of a metal T2Z orbital and a antibonding orbital. Okay, as I have discussed in the last assignment, that a pi star antibonding orbitals is available for donation from the metal. Okay, the situation is called back bonding. Okay, right. So because the ligand it donates sigma electron density to the metal, and the metal donates pi electron density to the ligand. Okay, so this ligand is thus acting as a sigma donor and pi acceptor. So if I talk about this ligand, okay, so here basically whenever I will discuss the sigma the MOT diagram for this carbonyl. Okay, so these are the p orbitals. Okay, and this if this metal is having a high electron density, basically whether it is in low oxidation state, so this or this electrons can partially overlap with this one. Okay, so this is called back bonding. So that's why these the tendency of transfer of these electrons from this to the the ligand is more. Okay, so that's why it is a sigma donor pi acceptor ligand. Okay, so the next two problems, that is the ligand in which the metal T2Z orbital participate in d pi d pi pi bonding is. Okay, so here the orbital of metal d, basically d orbital, is making bond, or you can say making overlap with the d orbital of the ligand. Okay, so you have to identify which ligand will be the appropriate one to participate in this bonding. Okay, and the second one, the symmetry required for the ligand group orbitals of pi donor ligand to have pi interaction with the metal d orbitals in the octahedral geometry is, it is T2Z, A1Z, EZ, or T1U. Basically, these three orbitals are already involved in the sigma bond formation, so you can easily opt out other options. Okay, so if you know the answer, just type in the chat box, please. And if I discuss about the first one, that is d pi d pi bonding. For that bonding, your ligand should have a vacant d orbital. Okay, at least it should have that cell in which the d orbital can exist, like 3D. Okay, so just identify among these and tell me, please. Okay, so as I have discussed already, so molecule with central atom having d valence cell. So in this case, the sulfur is having a d valence cell, so it can participate in the d pi bonding. Okay, So it is a very simple thing. And the second one, the T2G set of ligand orbitals are available for pi interaction because other these three, they did not match with the symmetry of any metal orbital, so they are not further involved in the pi bond formation. Okay. Okay. So there are three ligands given here, and you have to identify which will be working as pi acceptor sigma donor, only sigma donor, and both pi donor and sigma donor. Okay. And the second one is ligands with good pi donor and weak sigma donor properties are very strong field ligand, moderately a strong field ligand, very weak field ligand. Okay, so if you know the spectrochemical series, okay, so they are arranged in a way that first the weak ligands are put up, and then the moderately strong field ligand, and then the sigma donor pi acceptor ligand, that is strong ligand. Okay, so try to solve or and send me the answer. Please try. CO ligand and CN ligand, you already know these are sigma donor and pi acceptor. Okay, because these are strong ligands, so you can easily match up. Okay. And hydride ion, since it is having a 1s orbital, okay, and one negative is also there, so both electrons can be accommodated into the same orbital, and it can involve only in the sigma donation. Okay. And what about this one? It can also donate sigma as well as pi. Okay. Right. So what about this one? That is good pi donor, since the strong ligands are those who have a good pi accepting tendency. Okay, so they will be very weak field ligand. Okay, so here is the explanation. Hydride ion acts as the only sigma donor, as no ligands or orbitals are available for bonding interaction with metal orbitals, and these cyano ligands act as both pi acceptor and sigma donors. Okay, and this hydroxide ion acts as both pi donor and sigma donor. Okay. And as I have discussed about the second one, the ligand which are good pi donor and weak sigma donor are very weak field ligand, and generally constitute the extreme left position of the spectrochemical series. Okay, so they possess field orbital available for overlap with, and p bonding interaction reduces the energy gap. Okay, in the last assignment I have discussed the MOT diagram in case of pi donor and pi acceptor ligands. Okay, so you can just study that and choose the correct answer. Okay, so basically this energy gap, since the energy gap is reduced, okay, so the ligand field strength is also decreased. So that's why uh, they have they have been placed at the extremely left position of this spectrochemical series. Okay, so basically they are arranged in the order of the energy gap between these orbitals. Okay, so the next one is you have to identify the inert complex among the following. Okay, I think you are already familiar with inert and labile complexes. And the second one, also you have to choose the most inert metal center. Basically here, uh, the different configuration in the different environment, that is high spin and low spin, are given. Okay, you have to identify the most inert metal center. Okay, here it is vanadium plus 3, it is chromium plus 2, and nickel plus 2, and vanadium plus 2. Okay, so it will be D2, it will be D3. Okay, and it will be D4. And what about this one? D8. Okay, since all are the uh, low, since there is a low field ligand. Okay, so just fill these electron configurations and identify the inert complex. Okay, just try. It will be T2Z2, right? It will be T2Z3 is E1, and it will be T2Z3 is E0. Okay, and what about this one? It will be T2Z6 and EZ2. Okay, so if you are having electron density in the easy orbitals, and you already know in the octahedral complex formation the ligand approach along the axis. So here inter-electronic repulsion will be there. So that's why the complex will be labile. Okay, and in case of D2 is always a labile complex, and this T2Z3 is inert because it is having a negative crystal field activation energy. Okay, and what about this one? Just fill them, and you will be getting the information. Okay, let me check if anybody have given the answer. Okay, so here is the explanation. The inert complex is this vanadium plus 2. Okay, the last one, greater the loss of crystal field stabilization energy, complex will be more inert. Okay, and D3 metal ion will have highest loss of CFSC during intermediate formation, hence most inert. Okay, so how you will be getting the idea of this highest loss of CFSC? Okay, so if there is any octahedral complex and it reacts with any incoming ligands, so whether it will undergo through associative mechanism or dissociative mechanism, right? So it will acquire a new geometry like this one, or this one. This is octahedral wedge structure. Coordination number here is 7, and here is coordination number is 5, and here is 6. Okay, so if the geometry is changing, the crystal field stabilization energy will also be changing. So that's why the loss in the field stabilization energy can be easily calculated. Okay, and what about the second one? The electrons in the easy orbitals for octahedral complexes leads to relatively weakly bound ligands and hence may be easily replaced. Okay. So D9, high spin D5 and D6 are comparatively labile and will undergo fast ligand displacement reaction, but the low spin D6 metal complexes are inert and undergo slow displacement reactions. Okay, so if you fill the D6 in the low spin, it will be like this, and easy will be 0. So there will be no inter-electronic repulsion, hence it will be the inert complex. So it will undergo a slow ligand displacement reactions, right? So just select uh, which one. So D6 low spin. Okay. Apart from that, you can see here is also electron density in easy orbitals. Here also, and here is also. Okay. So where the inter-electronic repulsion occurs, there is a more tendency of complex to be labile because that bond length is basically increasing. So that's why the lability occurs. Okay. So the next one, among the following, both thermodynamically and kinetically stable complexes. Okay, you are given three complexes, and you have to identify which one or all of these are thermodynamically and kinetically stable. Okay, so if whenever we talk about kinetically stable, okay, we talk about labile or inert, right? And whenever we talk about thermodynamically stable, we talk about the energy formation constant. Okay. And the second one is among the following metal complexes, the most labile one in terms of this exchange reaction. Okay. So which one will be having, which one will be showing the most lability in terms of this cyanide exchange. Basically, this is isotopically substituted cyanide to know whether this ligand is exchanged or not, right? To basically differentiate from this one. Okay, so you are given four complexes. Just identify which will be the most labile one. One is tetrahedral, other three are octahedral complexes. Okay, so these are the explanations. Okay, so for metal complexes, the stability and reactivity are described in these terms. Okay, in particularly the term stable and unstable are related to thermodynamic aspects, when labile and inert are kinetic aspects, as I have already told you. Okay, so these all complexes are thermodynamically stable with the value of these. These are the experimentally determined thermodynamic stability constant, that is 29, 40, and 42. Okay, so they all are thermodynamically stable. Okay, if you are interested in their kinetic stability, just write their electronic configuration, and you will be getting the information what configuration they have, and whether they will be showing the lability or inertness. Okay, since all ligands are strong field complexes. Okay, here we will not be talking about the lability and inertness, because it is the question is asking about the stability. Okay, so whenever you will be discussing about stability, it is related to some thermodynamic aspects. Okay, and about the second one, I have already given the information that this tetrahedral complex is more labile, because it is already having enough space to accommodate the incoming orbitals, sorry, incoming ligands. Okay, so the tetra coordinated is the most labile one than the others, because it possesses enough enough space around the metal cation to accommodate the incoming ligand into the coordination sphere to form the activated complex. Okay, clear? Right. So the next one, in a octahedral configuration, total how many p orbitals are available in the system? I think you have already discussed. Okay, so just choose the answer and please tell me, because there are 18 orbitals total. Okay, and p orbitals, if I talk about, you just, and about in the second one, you should be familiar about this carbon monoxide molecule and its MOT diagram, molecular orbital diagram, and you have to identify the HOMO, basically the highest occupied molecular orbital. Okay, so here are some orbitals given here. That is, first is S antibonding, S2pz. Okay, and it can be bonding, antibonding, or non-bonding, right? So tell me if you know the MOT diagram of carbon monoxide. Otherwise, I will be discussing that. Okay. Yeah. Okay. So yeah, according to the group theory, there are the combination you are getting, as I have told you, that is T1Z plus T2Z plus T1U plus T2U. Okay, if you add basically the D's and JC, that is 3, 3, 3, and 3, that is 12 orbitals will be there, and the two orbitals contribution from each six ligand. Okay, each of the six ligand, which are basically perpendicular to the p sigma. Okay, right? So the 12 orbitals will be there. And if I discuss about this MOT diagram of carbon monoxide molecule, here you can see basically uh, the carbon is having 1s2, 2s2, and 2p2. Okay, so whenever this carbon and oxygen combine, they form some hybridized orbitals. Okay, since this you can see this spz, these are the this is the spz hybridized orbital. Okay, and why the energy of this oxygen orbital is low? Because oxygen is very highly electronegative atom, so that's why this energy is lower. Okay, so if you are having px, py, and pz orbitals and s. So s basically combined with this one, because this the symmetry of pz orbitals is basically matching with this one. Okay, so it forms the new hybridized molecular orbital. Okay, so same in the case of carbon, that is spz, because two orbitals are combined. So one is 2 spz here, other is here. So basically, because the energy gap between this and this one is very large, so it will remain as a non-bonding orbital. Okay, and apart from that, if you see that 2px and 2py and this 2pz, okay, basically these two orbitals are combined and hybridized orbitals are formed. Okay, and thereafter they combine with each other. Okay, so you can see one sigma bonding orbitals is formed here and other is anti-bonding. And similarly with the px and py, two bonding orbitals are there and two anti-bonding orbitals are there, but this one is non-bonding. So if I number it, sigma 1, sigma 2, and sigma 3, basically this is the third sigma orbital. Okay, and if you identify the HOMO, that is highest occupied molecular orbital. So this is the highest occupied orbital, and it is also called HOMO, and it is coming from spz. Okay, so this spz will be the HOMO for this carbon monoxide molecule. Okay, clear? Any question? Okay, yeah. So moving forward to the next two problems, that is among the following which is not a p acceptor ligand. Okay, that is you can say PR3, and R can be any group. Methyl you can put over here. Carbonyl, that is carbon monoxide molecule, you can as a ligand, since I am talking about, and NR3. Okay, so here you can also put methyl group. Okay, trimethyl phosphine or trimethylamine, and last one is the azide anion. Okay, and the next one is asking about the rate of exchange of water present in the coordination sphere by this isotopic substituted water in these complexes. Okay, so whenever we talk about the water exchange, first we discuss about oxidation state of the metal. Okay, then size of metal ion, and third is charge to size ratio. Okay, And the last but not the least, that is John Taylor distortion. John Taylor distortion, because if there is John Taylor distortion, the bond will be, uh, you can say, the bond strength will increase, and the bond, you can say, the bond will be elongated. Okay, so the rate of exchange will be faster. Okay, so you have to keep these 4 points in your mind while identifying the rate of exchange of water. Okay, so tell me if you get the answer, please. First write down the electronic configurations. That is, it is D9, and what about this one? It is D5. Okay, so here you can see a trend. All the metal ion in +2 oxidation state. Okay, so what you can do, just compare their ionic radius. Okay, and if the radius is higher, you will be getting a high exchange rate, because uh, the metal having low size will effectively participate in the bonding with this ligand. Okay, and that will, the bonding will be very strong, so that complex will be mostly inert. Okay, and if I talk about this one, that is D9, and write down the electronic configuration, that is, you can see easy is unsymmetrically filled here, so strong John Taylor distance distortion will occur. Okay, so if John Taylor distortion will occur, so these bonds will be elongated, so that's why the rate of exchange will be much faster. Okay, so it will be having a higher rate of exchange. And in other, apart from that, in all these three cases, you will see the easy is symmetric. Okay, because the number of electrons is basically increasing in the T2C orbitals. Okay, so first is having higher rate, right? And what about the other one? Just compare their ionic radius. So manganese will be having higher than iron, then nickel. Okay, so this will be the right answer for this. And what about this one? So basically, okay, let me discuss on the next slide. So NR3 and PR3, if I consider is as methyl. Okay, so here these pi orbitals can have back bonding. So that's why the tendency of accepting the electrons from metal is rising here. So that's why the pi acceptance property is there. Same goes for this PR3. And carbon, this molecule is, you already know that is, it is a sigma donor pi acceptor. Okay, but if I discuss about this N3 negative I, okay, so it is basically a linear molecule containing sp hybridization. So basically it already have very high electron charge density. So why it will accept the pi electrons, the p electrons from other metal? Okay, so that's why it cannot work as a p acceptor ligand. So that's why this fourth one is the right answer for this. Okay, yeah. So the next is the last of this session. You have to identify the rate of exchange of cyanide ligands in this complex. There are three complex. First is tetrahedral complex. Other are uh, octahedral complexes. Basically, both are having plus 3 oxidation state but different electronic configuration. Okay, so you have to identify the lability and inertness. Okay, because it is already clear that it is highly labile because it is a tetrahedral complexes. It has enough space to accommodate the incoming ligands, so there is not an issue. But what about this one? Just compare, because it is a D4 configuration and it is D3. Okay, so D3 is inert, and what about D4? Okay, just comment on it. Thereafter, I will explain why the rate of exchange will be higher in which case, and which case it will be lower. Okay, so I have discussed this concept multiple times in this session. So I expect the answer for this particular questions from your side, please. Okay, yeah, okay. So as I have indicated that D3 is inert among these, so the rate of exchange will be lower in this case. Okay, so the answer is the last one. Okay, so let me discuss it further, right? So the kinetics and mechanism of metal complexes can be better understood by making a distinction between thermodynamical terms, stable and unstable, that is already discussed. So, okay, so these three complex, if I take, okay, so leave it because it is a tetrahedral and compare this one. So if you see the T half life, okay, so it is 30-second only in case of tetrahedral complexes, but in case of MNC tetra cyno complex, it is 1 hour. But in case of this chromium, that is basically D3, it is very high, 24 days. So this complex is inert as compared to this one. Okay, so in the strong field octahedral complexes, those containing metal ions with the D0, D1, D2, D9, and D10. These configuration either have a negative value or zero value of crystal field activation energy. Okay, so such complex would therefore be labile. But the complexes with metal ion configuration of T3, T5, T6, and D8 have a positive crystal field activation energy, so they will be uh, therefore they will be slow to react. Okay, so the order of reactivity, if I write here in the strong field octahedral complexes, that will be D6, then D3 is just equivalent to D8, and then D5. Okay, so they are slow, but if I compare the reactivity, it will be like this. Okay, and what about D4? D4 will be uh, having either negative value of crystal field activation energy. So they will be labile, right? So I think this session and discussion is clear to you. If you know, if you are having any problem with respect to this assignment, just let me know. uh, on daily basis I usually post the videos along with the pdf of the assignment in the drive link. Okay, you, those who have not attended, you, they can check there. Okay, so thank you very much for attending the session. Have a good day.